and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on thermodynamics. Previously, we learned about the relationship between the second law of thermodynamics and the cooling process of refrigerators. We examined the working mechanisms of a refrigerator and explained how it functions. Today, we will be discussing the relationship between the second law of thermodynamics and entropy. If you are ready, we will begin. First, let us do a review activity. Can you define entropy? Write your answers down, and I will see you in a few minutes.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello, students. I am sure you found this activity easy. A few lessons ago, we defined entropy as a measure of disorder found in a system. However, understanding the concept of order and disorder is also critical to understanding entropy. As an additional question, can you define disorder, students? You may begin.
Students, Let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back. I imagine you found this simple enough to define. Disorder, or chaos, is defined as a lack of order or arrangement. Consider the second law of thermodynamics in relation to entropy. It states, no process is possible in which there is an overall decrease in the entropy of the universe. This means that if this law is true, energy can only exist in situations where entropy increases. We discussed how this is possible with a few examples of reversible and irreversible processes in our previous study of entropy. We explained how transferring water back and forth from a full glass to an empty one is not a reversible process because of a multitude of smaller factors which may be contributing to an increase in entropy. Let us look at a more detailed example. Consider this vial of water. In the middle of the vial, a divider separates 5 bromine particles on the left side from the pure water on the right. Once the divider is removed, the particles are allowed to move freely to any location within the vial. These particles may go in any number of random directions. Since entropy is a measure of disorder, it is equal to all of the different possible ways the system may be arranged. Before the slide was moved, our system was ordered. As there was only one possible arrangement for the bromine particles, they were all in the left side of the vial. Once the divider was removed, there was an increase in entropy in the system, as suddenly there were 32 possible arrangements in which the particles could exist. This image shows the different possible arrangements. If we're trying to determine the probability of the particles on the left side coming to a state of rest on the right side, we must make a few calculations. First, there are 5 particles. There are 2 states in which these particles can exist: at rest on the left side or at rest on the right side. Thus, the way in which these particles might distribute is 2 times 2 times 2 times 2 times 2, or 2 to the power of 5. Therefore, in this system, there is a 1 in 32 chance that all the particles will be in a state of rest on the right-hand side of the vial. The same ideas about entropy and the second law of thermodynamics are not just true in prescribing the direction of time when observing particles of gas. It also helps describe the process of photosynthesis and the functionality of machines. Furthermore, it explains why energy tends to spread out in the process of heating. Just as the spreading of particles in the vial is an increase in entropy, the spreading of random kinetic energy through heating is also an increase in entropy. If we are not observing a gas, then we evaluate the change in energy of a system by the movement of its quanta. A quanta is a set amount by which an atom can increase or decrease its energy. It is the behavior of quanta that is similar to particles of gas. If all the quanta that exist in a system are held by a small number of atoms, then the number of possible arrangements of the quanta is small. However, if the same number of quanta were distributed amongst a larger number of atoms, although the total energy of the system is the same, the number of possible arrangements increases. Therefore, so does its entropy. Remember that in the study of entropy, the system is any object, but the surroundings include the entire universe. This is important to recognize. Consider the refrigerator we examined in our last lesson. By doing work on this system, energy is transferred from a colder body to a hotter one. Recall that this process was not spontaneous. That is to say, while the entropy inside the fridge decreases, somewhere else in the world, a lump of coal was burned to provide the necessary electricity. Essentially, the entropy of the universe increases to a greater proportion than the decrease of entropy in the fridge. Students, are you ready for our last activity? Please complete the following statements.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, everyone. Let us now complete the statements together. No process is possible in which there is an overall decrease in the entropy of the universe. This statement is the second law of thermodynamics. Entropy is the measure of the amount of disorder in a system. Quanta are the set amounts by which atoms can increase or decrease their energy. Entropy helps to explain the direction of time and the spreading out of random kinetic energy through heating. Were these your answers, students? Great work. This concludes our lesson for today. We have discussed entropy and its relationship with the second law of thermodynamics. Until next time, thank you, teacher. Thank you, students.